Dan is not a stranger at all to us. Well, his most important roles to us is he's one of the program directors managing our award. And he's been persistently supportive, coming to our meetings and conferences, and we even managed to confuse him how often we run our international conferences. We were chatting this morning. But Dan has a long, distinguished career. As you all know, he collected all of his 3 degrees from BS to PhD from Northwestern University in Chicago in electrical engineering. His expertise largely fall into parallel and distributed computing programming language, as we were mentioning that. He's now at NSF. His home is at University of Chicago in the Computation Institute. He's a senior fellow there. In the interest of time, we'll just pass the floor to Dan. Thanks very much. Yeah.
Okay, thank you. So I almost feel like I've been set up to disappoint you a little bit, which I hope that I won't do. I don't think that I'm not going to be able to tell you really, I don't think, how you should do what's necessary in order to educate the CyberGIS community of the future. I think what I can tell you is what other communities are doing and what you might learn from and what NSF can help by supporting. But the answers that come out really are really up to you to decide. And I guess I would say that in general, the philosophy at NSF, at least informally, I don't know if this ever gets written down on paper, is that we tend to respond to what the community says that they want to do. So if a large group of people come together and they say that we think that it's really important to have a program that does this, and we've all been working in this area, and here's the evidence that we've been working in this and working together in this, then it's reasonably likely that NSF will find some way to support an activity. So I think maybe that's a message that I want to kind of leave from the beginning, which may or may not carry through the rest of the slides. Is that it's really up to you to say what you think is needed and then to convince people at NSF that that's the right thing. And then it's the job of NSF actually to find the money and to find the structure in order to do that. So with that, let me tell you about some of the ways that we've been trying to do things like this with some other programs in some other areas. And so I'm going to talk really about 2 things, about software and education. And I'm going to talk about it in the context of what's now ACI, the Computer Science Directorate, and the Division of Advanced Cyberinfrastructure, which at one point when I started was the Office of Cyberinfrastructure, but has been combined in the last year and a half. I'm going to, I guess, talk from the perspective of ACI, but it's a little bit wider than that. A number of the things that we're doing are really kind of cross NSF. And so I think that while different parts of NSF have different messages and different interests, what I'm going to try to talk about is something that spans a number of those areas. Okay, so to start off with, I apologize if people have seen this before, but I just want to kind of explain why ACI, the Division of Advanced Cyberinfrastructure, is there and where infrastructure comes into science. So we have problems like hurricanes that affect people. The picture on the bottom right is Hurricane Katrina. The dots are the location of the hurricane every 6 hours, and the lines are a variety of forecasts that were made at that time. And what you can see from this is that until some point around there, you don't really get the convergence in the models that says where the hurricane is going into New Orleans. And doing this work in order to make these predictions and to figure out basically how are people going to respond is fairly complicated. And it's complicated because there's a lot of stuff going on. There's a lot of physics that has to be modeled in terms of the atmosphere and the ocean and the coast and the vegetation and the soil. And these models use sensors and data as inputs. Some of the sensors are on buoys, some are satellites, some are aircraft. And then if we actually want to think about what's the impact of the hurricane going to be on people, then we have to really understand people as well. And so we have to understand what people have built, where the people are, and how they behave in some sense. Right, so the hurricane is forecast to hit New Orleans in 36 hours. What does the average person do? All right, do they plan to leave? How are they going to drive? Are they going to get gas? Are they going to pick up a pet or drop off a pet? So lots of different questions. And in particular, these things can also be combined. So as the storm surge starts approaching the land, some of the roadways may be closed because of water. And then what's the effect of that going to be? So this is really a fairly complicated interactive problem. The infrastructure that's needed in order to do this then is a variety of different pieces. There's the urgent and the scheduled processing piece, right? So the hurricane is first forecast and suddenly things have to spring into action to start doing forecasting and prediction. But as the hurricane is getting closer, there's kind of a regular cycle that people fall into where there's new forecasts of wind coming every 6 hours, and those wind forecasts then trigger another set of activities. There's the actual software applications for all these different pieces, and then the workflows that actually put them together. There's the networks that are used to bring the data together to actually make the computing work at a distance. The decision support systems and the visualization systems that take this information and turn it into something that people end up using in order to try to decide what to do, whether they're government officials or the public. And then data storage and interoperability. So the point of this is that all of those pieces on the bottom, those infrastructure pieces, are not specific to this problem, right? They could be reused in a variety of other problems as well. Hurricanes in other places, potentially some of them are in tornadoes, some of them could be used for earthquakes, some of them could be used for astronomy and other sciences. Some of them could be used for marketing of where a fast food restaurant is going to put their next location. All right, so these are really infrastructure. They're not specific to this. And this example is what I call the top big science. It's a bunch of people coming together in order to solve a particular problem. On the other side of things, we have the long tail scientists and the long tail of science. And the graph that's on the top right, let's see. Top button. Yeah, okay. So the graph up here basically is showing award size versus the number of awards for NSF grants in 2007. And what you can see from this is that there's a small number of large awards, but there's a very large number of small awards. And all the people that are kind of off in this area need to use infrastructure in order to basically do the science that they want to do and not focus on repeating the computational pieces that other people have already done. And the challenge is that they can't often afford to have a person that's a software specialist and a data specialist and a computing specialist and a networking specialist. All right, so we have to take all of those things and try to bring them into the infrastructure so that the scientists that are getting small amounts of money to work on their science can really work on their science and not on the infrastructure pieces. And so the question here then is, how do we outsource or automate time-consuming and common processes? And there are tools that can help do this. Globus Online, which is actually now Globus, is one example that can do this for data management. Science gateways, like things like NanoHub and Cypress, can also do this and help with this. So if we put these things together, we can come up with a definition of cyber infrastructure, and this one's from Craig Stewart. And it says that cyber infrastructure consists of computing systems, data storage systems, advanced instruments and data repositories, visualization environments, and people, all linked together by software and high-performance networks to improve research productivity and enable breakthroughs not otherwise possible. So if you think of this as a definition of cyber infrastructure, then you can also think of a bunch of elements within the infrastructure. And the elements then have some place in the infrastructure. They're part of the infrastructure. The elements are developed by individuals and groups, often internationally. They're developed for a particular purpose, and they have a particular community. And the reason I'm phrasing things like this is really what NSF tends to support, is the elements of the infrastructure. And we think about kind of the answers to these questions when we decide what we're going to support. So the way this actually has developed over the last few years is that there's an activity called the Cyber Infrastructure Framework for 21st Century Science and Engineering, or CIF21, that is a cross-NSF portfolio of activities that try to bring the cyber resources together across a number of areas. And when ACI, which was OCI at that time, started working on this, it set up a number of task forces to report to the Advisory Committee on Cyberinfrastructure, the ACCI, and to talk about basically what's needed in a bunch of different areas. And all of these areas together are what make up cyberinfrastructure. And those areas are campus bridging, cyber learning and workforce development, data and visualization, grand challenges, high performance computing, and software for science and engineering. And each of those task forces had a report that they issued, and those reports are available. They're something like, I don't know, between probably, 40 and 80 pages each, so kind of lots of content about basically what those task forces, which were assembled from people in the community with perhaps one NSF representative on each one, said were needed in order for work to go forward in different science disciplines. Out of that then, again, ACI or OCI at the time tried to look at those and create our own vision and strategy report saying, how would we respond to those task force reports? What programs did we need to do? What activities did we need? And so this was done, and there's 3 of these as examples here for ACI, which in this case is Advanced Computing Infrastructure, which really is HPC, for software and for data. And then in software, we went a little bit further and we tried to create a document that said, if you as a PI are interested in developing software, can we tell you basically which programs we have and how you should figure out which program would support the activity that you want to do? And we're in the process of doing one of those for data as well, but it isn't, it's not a public document at this point. Okay, so these vision and strategy reports, these 3 things that are in the middle there, they all, I would say, look somewhat similar to each other. They have some common components. And I'm going to talk about the software one, but you could really, instead of software, say data, or you could almost say anything else. And each of these really has 5 components, and the core of the components is to have an ecosystem that provides the capabilities needed, the different infrastructure pieces that are needed. So in this case, it's a software ecosystem that provides the software capabilities that are needed for science. In order to have this ecosystem, we need to have new things coming into it over time. So we need to have foundational research, either in algorithms, in geosciences, in computer science, in math, in different areas. And these research projects then, often the successful ones, get turned into software, and that software is framed in a way that can be reused by a lot of people, and then that gets pushed up into the ecosystem. We also need, in some cases, to have activities where we make sure that the ecosystem is being used, that it's meeting the needs of the community, and that we have the right incentives for people to use the software that's available rather than developing their own. One of the things that's actually extremely hard about this, and I'm not going to talk very much about in this talk, but I'm happy to talk separately, is that in order to actually get this to work, the most challenging things really are policy related. And in terms of software, the particular challenges are how does academic culture work with software? How do we make sure that software is openly disseminated and used, that it's reproducible, that it's trusted, that it's curated, that it's written and maintained sustainably, that we have good governance for software projects, that we're able to cite software, and that we're able to attribute software authorship to the right people, and we can build really into the academic system the fact that there is software in this case. But you could, again, say the same thing for data. You could say the same thing for computing infrastructure. And then the last piece of this, and this is the one part that I'll mention that has this kind of double-headed arrow, is the education piece. And so the reason that the arrow has is a bidirectional arrow is that we need to use the ecosystem to make sure that we can educate people that can use software effectively, that can use infrastructure effectively in order to do the best science that they can. But we also have to make sure that we're educating people so that they're going to be able to generate the next generation of software or next generation of data, and that they're kind of embedded in the culture that brings them into this and makes them want to participate and want to do better things than they would otherwise. Okay, so having said that, let me move on to the kind of the education part of things. That's really kind of all that I'm going to say about software specifically. When we think about education, in ACI particularly, we think about workforce as an element of cyber infrastructure. And so we think about different pieces. We think about cyber scientists who are cyber infrastructure focused, who are able to develop new capabilities. Again, these are the people that are doing the foundational research and building the tools that are going into the ecosystem. These are the people that are building the CyberGIS systems and the other pieces at this point. We think about the scientists that are going to be able to use these capabilities. All right, so this is the mass of day-to-day geoscientists, GIS scientists. I mean, in some sense, this is the Esri customer base. Right, this is the people in lots of other domains as well. And again, these are the people that need to be able to use the tools that are there and use them effectively. And then finally, we need to have the staff that actually makes the systems work. And so in some cases, this might be professional staff at NCSA that have the capabilities to do this. This could be people in computing centers at universities. This could be system administrators in departments. It could be professional staff that are associated with projects. But in any case, we feel like there really are these three separate needs in terms of education and workforce development that are needed, of the developers, the users, and the people in the middle that make everything work. Okay, so let me give actually a couple of just brief examples of some cyber infrastructure projects that are education related. So the first one is one that's called I2U2, Interactions in Understanding the Universe. And this is an educational virtual organization that's intended to strengthen education and outreach of a bunch of science experiments at US universities and labs. In particular, it's in a few different areas related to physics primarily. CMS, one of the LHC experiments, there's a cosmic ray activity and a LIGO activity. LIGO is the Laser Interferometric Gravitational Wave Observatory that's looking for gravitational waves. So these are all kind of astrophysics in some sense. The idea of what this project does is that it creates and maintains an infrastructure and a common fabric that can allow people to develop hands-on laboratory course content and to provide interactive learning experiences to bring aspects of those experiments into a virtual laboratory. And they have two different kinds of virtual laboratories that they support. E-labs, which are things that can be used in classes and classrooms and use web tools, and I-labs, which are things that are more physical interactive interfaces, things that you might see in a museum where you can turn a dial and understand what happens. But maybe that wouldn't be the right thing to have in a classroom. So the project overall is a collaboration of scientists, computer scientists, and educators with the aim, again, of growing and sustaining the science workforce and promoting public appreciation and support for the large-scale national science projects. And there's a website here if you're interested in more information. Again, I think it's an interesting example to look at how cyber infrastructure is really brought into education. Another thing that I wanted to mention is a program that's going on currently at the University of Chicago called Data Science for Social Good, or DSSG. And the thing that's going on here is that this is a summer program for data scientists who are interested in doing something for the social good to come together and to work on data mining, machine learning, big data, and data science projects that will have some impact that benefits society. There's 48 undergrad and grad students that are currently in Chicago working on this. They're working in teams of 4, in each case with a government or a nonprofit mentor. And they're trying to tackle real-world problems like in education and health, in energy and transportation. And again, there's a kind of a website here that talks about more of what's going on there. This is, again, I think this is quite a different example, but the thing that's interesting here is that, and I'm not really saying it here, is that there's a kind of a core cyber infrastructure that's needed for all of these people to work together, and that's really the thing that makes this common and that makes this one program, right? The social part of it is the purpose. The cyber infrastructure is the thing that ties all the different projects together. Okay, so if I think about these two things together, these two examples, the things that are common about them is that they bring together students and educators and teachers or mentors. They either use or build tools. In the case of U2I2, those tools are pre-existing in general. In the case of the DSSG example, some of them are pre-existing, but some of those activities, the students are there to build new tools, and that's really the outcome of those projects. And they have tremendous impact on the students that participate, and ideally, they have large impacts as well on either science or society, depending, again, on which side of things we're looking at. So I think if we think about these things, in order to do things like this, we need kind of a variety of different pieces, right? We need education, which is I would say is the stuff that happens in the classroom that teaches people how to think and how to answer questions. We need training, which I guess I would distinguish from education as being kind of how to use a tool or how to do something that's more specific and less general. We need the materials that are actually able to teach these things. We need the tools that are used in these pieces. We need the funding and the organization to actually make these projects happen. And then we need inspiration or motivation that makes people want to do them and makes the students want to participate. Okay, so I'm going to kind of just go through some examples of these different activities and talk about where some things I see that are interesting are happening. And so the first thing I'm just going to mention is some curricula activities that are happening in computer science. In terms of parallel computing in computer science, there's this very nice TCPP model curricula that one of our participants is quite heavily involved in fact, is leading. It's really a way of trying to say, basically, parallel processing is important in computer science. How do we inject parallel processing into the existing curricula, right, without necessarily replacing other things that also are still important, right? So how do we bring in new things in a way that actually adds to what's available, but doesn't give students something more that they're not able to add another class or something like that? There are other things that are also going on in this area. There's a new curricula at Carnegie Mellon for parallel computing. There's a lot of work that Intel is pushing in this area. And so in computer science and parallel computing, there are these variety of things going on where basically different groups of people are coming together saying, we need to make changes in what's happening in education because the landscape of technology has changed. How do we do that? And these are examples of what's happening. There's similar activities in distributed computing that I would say, are less accomplished, but similarly intentioned at this point. And then if you look at parallel and distributed computing together, there's this large ACM IEEE Computer Society activity to really to work on both of these things and to try to figure out, in terms of a group of educators and a group of professionals, what's needed in order to change the education system to make it relevant to where technology is today. And so these are computer science examples, but I think the things that are common that can apply outside of computer science are that there's a group of concerned faculty that are coming together that are led by usually a small number of people initially, but through some number of activities, they bring more people in and they convince more people this is the right thing to do. They work through what the needed changes are, and again, the changes can't just be additions because we can't keep adding more courses, right? We have to make changes rather than additions here. They work with early adopters in all of these cases, and they take the lessons from those early adopters and then they update and expand, and eventually the idea is that these things will really proliferate across the educational landscape. And I would say in all of these cases that I'm giving, it's probably too early to say if they're successful, but they all seem like they're on a path to success at this point. There's other activities that are going on. There's things like the HPC University or HPCU, which is a virtual organization that's intended to, not for computer science necessarily, but for high performance computing, deliver the education and training material that's needed to provide resources and to bring people together again in order to figure out what the needs are, what the requirements are, what needs to be built, and build stuff and try it out. So again, I'm giving a couple of examples from computer science because that's the area that I know the best. I'll mention that there's something called the National Science Digital Library, or NSDL, that actually maintains collections of things, and if you build things, you can put your components into this, and then other people can see them. This is, I guess, I don't know, I would say that one of the issues here is that there is this repository, there are other repositories. It's not clear to me at any time which repository actually has material that's up to date. And how things are being maintained and how things are necessarily being reviewed or used. So maybe that's a challenge, but at least there are places where things can be put and shared that's more than just having something on your faculty or classroom webpage that other people may find one day. And so the searches on the bottom where I was just looking for either parallel or distributed in terms of instructional material for education in computer science, and I found like 138 parallel materials and 337 distributed materials at the time that I looked. So it seemed like there was a variety of things, and I kind of looked through a few of these, and there are things like modules and tests and presentations and lectures and things like that. Okay, so on the side of training, in terms of computing, I think there's actually a lot of computing training available. It's both synchronous and asynchronous, meaning you can do it at your own pace, or you can actually go and attend things or look at webinars. These activities are often led by centers and by universities that have computational research programs within Exceed or DOE or things like NCSA as examples. They're also supported by organizations like the Schiller Foundation. Some of them are aimed at users, some of them are aimed at educators, some are both. And some are fairly specific computational science, like spend a week and learn about molecular dynamics and the latest tools, or spend a week and learn about the latest material science tools. But some of them are much more general, like spend a couple of weeks and learn about parallel processing, or take a particular parallel processing course over a period of time. Okay, and I'll skip the bottom of that. The other thing that's interesting to me, and I think this was mentioned, I heard a couple of, either 2 days ago or yesterday, is software carpentry. And so I think this is actually quite a good example of a community-led activity that is, I would say, really is still on the training side as opposed to the education side, but is doing things that are very practical. And so the idea of software carpentry, and I apologize if this was really stated on Tuesday, I guess, is that this is a team of people that want to help researchers be more productive by teaching them basic computing and basic software skills. And it runs boot camps at dozens of places and provides material as open access for self-paced instruction. And the things that are taught are things like basically how to use a shell, how to use Python, how to use version control, how to do testing, how to do databases, things like that. The model that's there is actually quite interesting because it's this kind of expansion model where there's initial instructors who are in many cases still active, but the instructors teach people and then those people become the next set of instructors, and this is really how it spreads out across time. And this is also how the material gets better and better over time and becomes more useful. And things like material can be created and aimed at particular groups. So there have been software carpentry activities that have been aimed at let's say female graduate students as an example, or at people in particular areas of biosciences. Right? So you can take this and you can craft it for particular audiences and try to make it more either inspiring or specific or whatever the right term is in order to get those audiences to be more involved. All the material is open for use and improvement. And I guess I would say that the project in some sense is the coordinators between the people that want to learn and the people that want to teach right now. Another example of something like this is the Argonne training program in extreme scale computing, which was a general 2-week program for computational scientists to provide interactive training on skills and approaches and tools to really do computational science and engineering applications on the high-end systems that we have today and the ones that are coming in the future. And it's really something that fills the gap between the education that you get in classes and the work that a number of people will do. And it's done by Argonne specifically because Argonne wants to be sure that there's going to be the people available that can use these facilities in the future. And they recognize that some training is needed in order to make that happen. Okay, let me talk about then what some of the things that NSF does here to help support activities like these. So one thing is the REU program, another thing is the DOE division, the Cyberlearning program, and the NSF Research Traineeship programs. And I'm going to talk about each of these individually. I'm also just going to mention, and I won't talk about this afterwards, that NSF is usually quite happy to support workshops and activities either like this or particularly that are aimed at education and training. And also undergraduate and graduate travel to conferences. So when you have something that's going on and you have a conference that you're organizing that you feel like really is the thing that would be important for the next generation of students to come to, you can come to NSF and say, we'd really like to create a program, a track within this that's aimed at students and brings them in. And if you can help us fund this, all right, then we'll be able to bring in, I don't know, 20 students, 40 students, whatever the right number is, in order to do that. And so NSF is generally open to activities like that and to things like that, that again, that come from the community. Okay, so I'm gonna, again, I'll talk about some of these pieces specifically. So, the RU program research experience for undergraduates has two different models. It has the supplement model and the sites model. And on the supplement model side of things, this is the idea that, that you have a project and you want to bring some undergraduate students into your project that's already been funded. All right, so anybody that has an NSF project can apply for an RU supplement. And there's a particular date often that is recommended, but you talk to your program officer and you say, is this something that you would support? And most likely they will say yes. They may say that it depends on the time. They may say that they want to understand how you're going to select students to make sure that you're looking at diversity and you're not just kind of picking some people that you would already be funding. But in general, again, this is something that NSF is very supportive of, and it's, in the scope of things, it's a pretty low-cost item for us, and we're, I would say, pretty generous with this. So if you have a project that's NSF funded and you have an interest in having undergraduates work on it, please try this and see what happens. It's important in these activities to have mentoring, right? This is not something where you're just bringing a student in to help you do something, but the student has to get something out of it as well. And that's really the goal of the projects, is for both of these things to happen, for the student to be involved in research and to make that something that helps you and helps the student decide that they want to do more research in their future. Right, okay. On the sites side of things, so again, if you have a program and maybe across a bunch of different areas, and you think that that you might want to try to get in a pool of undergraduates and assign those undergraduates to a set of different faculty members over a summer, over some other period, but usually over a summer. This is what the RU sites activity is. It's intended to let a university create, or actually I think it can be a set of virtual universities as well, set up a program to bring in a set of undergraduates, let them learn something, let them help in the different projects, and let them learn from each other as well. And again, hopefully make them more interested in continuing in research as graduate students in the future. The Department of the Division of Undergraduate Education, as part of the EHR Directorate, is something that's interested in a lot of the curricular activities that I've mentioned. So this in particular has, the division has goals of supporting curricular development and preparing the workforce. And so they have a variety of programs that do different things. And again, in some sense, I guess I would say that there's a little bit of a danger at NSF that different divisions tend to get a little bit siloed. So just as an example, if you have somebody that's not an astronomer and they're applying to an astronomy program, there's some danger that the peer review process is not going to find them very believable or very capable of doing the work that's needed. I think that certainly is a danger in some of the things like this as well. But usually trying to collaborate and bring in people where you can bring in new ideas but maybe work with somebody in the field is a way of getting around that. And so in things like the DOE programs, if you can bring in somebody who really maybe is working in a school of education and try to combine that with some kind of GIS activities and try to do something that would be beneficial both to GIS as well as to the educator's role of studying education, then I think that would be something that's worth thinking about. The Cyberlearning and Future Learning Technologies program that's available now has a vision that says basically that new technologies are going to transform learning opportunities in all phases of life, and they're going to make it possible for learning to be tailored to individuals and groups, and that the best systems that are going to be designed for these purposes are going to be done so based on how people learn, on the science of learning. And so the aims of this program really are twofold. One, on the future learning technology side, is to really learn how to design and effectively use the learning technologies of the future. And then on the cyber learning side, to understand the processes that are involved in learning, where the technology provides the ability for the people that are learning to do something that they wouldn't be able to do otherwise. And so this is a solicitation that's out. and is looking for projects, and the projects really need to do three different things. All right, they need to do something that's innovative, they need to do something that advances understanding of how people learn in technology-rich environments, and then they need to promote how that's going to be transferred and generalizable outside of the particular domain where it's being used. So again, this is, I think, an opportunity where people in GIS or in other areas can propose projects, again, potentially working in collaborations. The last specific opportunity that I wanted to talk about is the Research Traineeship, the NRT program. And this is a replacement of the IGERT program, so if people are familiar with that, this is the new graduate training program, effectively. And the idea here is to develop transformative and scalable models for STEM graduate training to ensure that the graduate students develop the skills and knowledge and competencies that are needed to pursue a range of STEM careers. And there's a priority research theme here initially, which is called data-enabled science and engineering. My particular bias is that data-enabled science and engineering probably covers almost everything that happens in science. So I'm not really sure that this is a priority theme, but at least it's a way that you can phrase things to make it more likely that you'll get in the right area. But other themes are also allowed. So if for some reason you have some interest in doing something where you're going to bring a bunch of graduate students together and teach them over a long period of time through a variety of courses, and you can't convince yourself that it's data-enabled science and engineering, you don't have to. You can say that it's something else as well. So this is intended to, again, to emphasize the development of competencies for both research and research-related careers. So it's not just for people that are going to be faculty, but people that are going to be involved in research in other ways. And the idea of this is that universities use this to build a program, and then that program then will be sustained over time. So this could be what we would have called a computational science program in the past that goes across disciplines and across departments. I guess now we can't call it computational science. We'll have to call it computational and data-enabled science. But basically, I would say it's very similar. Okay, let's see, a couple of other things just to kind of close off the main content of this. So I want to just mention the Grace Hopper Celebration of Women in Computing and things like this. The TAPIA Celebration of Diversity in Computing, maybe less so. But these things that are really put together for particular segments of the community to inspire them in order to make them want to go forward and do better things, to do more research-related things. Again, Grace Hopper in particular is for women in computer science, but it doesn't have to just be computer science. And TAPIA is, I would say, is people from different backgrounds and ethnicities, again in computing primarily, but not just in computing. And the idea of these things are that they're intended to promote the attendees' work and to increase networking and mentoring, and to take people that may have a disadvantage in some way and try to give them an advantage that encourages them to continue and to deal with some of the lack of diversity issues that we tend to have, particularly in computing. Maybe, sorry, I'm just looking around. Maybe in GIS as well. Right. Okay. So having said that, let me kind of just go back to the education piece for a minute again, and say that I think the way that we're thinking about these things is that we're trying to really fill these three different roles of people and to make sure that the education and training opportunities are sufficient to do this. To make sure that we have the scientists that are going to be able to build the software and the data and the infrastructure of the future, to make sure that we have the scientists that are going to be able to use those things in order to do the best science and engineering possible, and to have the staff in the middle that make sure the capabilities work and that people can use them. So to conclude, I think that there's a lot of demand for trained people, for people in the workforce that have the right skills and abilities. I think there's a lot of demand as well for developers and staff and users. And in general, the demand on this seems to be on the education system, the academic system, but software carpentry is an exception, and I think things that kind of go across the academic system are certainly coming and are becoming more important at this point. In computer science, again, as an example, there are a lot of people that are trying different methods of teaching and trying to teach new things. And I think that they're starting to share their experiences in the lessons, and that they're moving towards some consensus on what should be taught and on how to teach it. Cyberinfrastructure really is a common point where all of these things are really being brought together. The big science, the long tail science, and education. And cyberinfrastructure then again has this role of being used in order to make the education work, and then also in being refreshed by the people that are being educated over time. And finally, I just want to say that I think that there's really a lot of opportunities here, and I and NSF, I think, are willing to support these opportunities, and the things that you or others need to do really are to get together, and in some cases maybe this has already happened here, but I'm not sure completely how much in terms of education, and to figure out really what needs to be done, and then to tell us what needs to be done, or to look for an opportunity where you can do it. And so with that, I'll say thank you. Okay, and
some questions for Dan. Yes, Tapani.
So, I'm Tapani Sarjakoski, Finland. I have a question. I'm in a process of setting something similar compared to CyberGIS in Finland. What are the positions from NSF for international cooperation?
yeah, so international collaboration in this area as well as in other areas is unfortunately more of a challenge than it should be. And I guess not as an excuse, but just as a reason, I'll just say that it's the problem is that there are too many bureaucracies that don't have working together as their primary goal. So I think I would say that that I and probably every other program officer I know at NSF are inclined to be supportive of international activities as much as possible. The problem is just actually getting that to happen. And so one of the things that can be done, and that can be done successfully, is that a team of people, again, comes together and they say, this is what we want to do, and they go to the funding agencies in each of the countries where there are activities, and they say, this is the part of the activity that's going to happen in this country, and we'd like you to talk to each other and to see if there's a way of putting all of this together into a single project. Sometimes that works. Sometimes it doesn't, just because of timing. One country has money available, one country has a deadline that doesn't match and has different restrictions. One country doesn't have a program that supports activities like this at all. So unfortunately this becomes difficult. There are activities like PIRE. I don't know if you've seen that one, but that's a program that's intended for international activities like this in some cases. There are particular opportunities for joint projects that are sometimes bilateral, sometimes trilateral, sometimes things like the G7 activities. So I don't think that there's a single answer, and I think that things are much worse than they ideally should be. But again, I think I would say, as I said before, that the thing that's probably the most important is to work with other people and figure out what you think the right thing to do is, and then try to talk to program officers individually and say that this is what we want to do, and basically turn it on us and tell us, like, can you guys figure out how we can do this?
Follow-up on that question. So is it the mechanism of a supplemental request through existing project for international collaboration feasible?
Yeah, so that's right. So again, this is an answer that's a question that's a little bit hard to answer in a single answer. The answer is, I mean, the desired answer is yes. I think, again, people want to support activities. There's just a question of cost and balancing budgets and trying to see what the priorities are. So I'm sorry, I guess I should say that the primary rule that NSF has is that NSF funds don't go outside the US, right? But that's not, I mean, so it's not strictly true. So NSF will fund people in the US to travel out of the US. NSF can fund people out of the US to come in the US and visit. If they can fund the US part of their visit, perhaps. But we won't fund research activities in another country in general, or education activities in another country in general. And so in terms of the supplements, again, if the supplement is something that fits into that, then we're certainly willing to support it. It's just a question of balancing the value that's going to come out of that versus the value of of having new projects coming through a normal peer review process as well. And so different program officers will have different ways of doing that, and some program officers will say kind of once a year they'll kind of build up a pool of things, and then they'll try to look at that pool. At the same time, they try to look at their other proposals and balance. Other program officers will have different ways of doing it. So again, it's just a question of talking to the program officer and trying to see. But in general, I think people want to do things like this as much as they can.
Hi, thank you. This was a great presentation. So I have a question about assessment and evaluation. So that's a big part of the evaluation of our grant proposals, is how good of an assessment and evaluation plan do we have? But in a lot of cases, people like me trained in CS and GIS are not learning science scholars. Mm-hmm. So could you talk a little bit about innovative ways and things you like to see in assessment and evaluation plans in terms of tracking students over time or activities that we should have them do?
So I think I would say that the immediate answer to that is no, I can't, unfortunately. And it's because it's not my expertise either, and so I know parts about it, some things about it, but the thing that I do actually is when we have projects like this, I look at program officers in those other areas and I ask them, do you think that the case that's being made here is a convincing case? Because I don't feel like I can judge that. And so the thing that I would say that kind of goes along with that then is that you really should be talking to people that are in the education school or in the assessment programs in the business school or in information sciences and trying to understand from them what the best practices are, and maybe even working with them as part of your proposal to make sure that those things happen. All right, in particular, independent evaluation from somebody that's not part of the project is often good if you can afford it. But I can't give you particular answers other than saying that it's something that's important to do. I completely agree. But it's one of those things that I guess I personally feel like it's hard. So when I think about this for me as a PI writing a proposal, it's very hard for me to do it, and I tend to depend on somebody else that knows it better than I do. And I guess I do that as well as a reviewer.
I just wanted to express my appreciation for your presentation also in terms of the breadth of information. And I wanted to focus in on the REU program. Mm-hmm. I think in terms of both as a broader program at a university or as a supplement to a grant, it can be so incredibly effective, especially for GIS students. Because I think, especially for GIS or CyberGIS students, they are looking for internships. They're looking for practical ways that they can practice their craft. They look to companies like Esri for these internships, and we certainly love the program that we have. But I think that we should encourage our students to look at REUs as another form of internship. And that's a message that we should send to them very strongly, because they have the idea that they need to go away from their campus or away from their department in order to have these kinds of experiences. And it seems to me that the REU fits that bill perfectly. Mm-hmm. Not that NSF has to say or do anything further, but I think for those of us who are on our campuses, that's a very important message. And again, especially for the GIS students who are looking to leave campus. So one of the things that I've told our current Esri interns here is that they should keep coming to us for internships, but that they should also look to their professors for some of these REU possibilities as well. So if this CyberGIS community or other parts of the GI science community can really tap into the NSF REU supplements or programs, I think that could be very fruitful.
Okay. Yeah, I guess, sorry, the only thing maybe that I would add to that is that in case this isn't clear, my experience when I was at LSU was that having an REU site program was a very good way of getting undergraduates interested in coming to LSU as graduate students. So I think it's beneficial for everybody.
Yeah. Thank you, Dan, for the great presentation. And my question is regarding the collaboration with industry and government. And you show us some successful models in education, but can you also talk about your experiences or your understanding of how to develop a successful collaborations in research with industry and in research with government agencies, and also the education opportunities?
Yeah, let's see, I'm trying to think about how to start with that one. Yeah, so, right, so I guess I would say that it's interesting to me at how difficult I think successful long-term collaborations with industry are beyond a particular faculty member with somebody that they build up a good relationship with. So if you have that, then I think things work well for quite a while. But if I try to think about programs, so NSF has this IU CRC program, right, which is intended to bring companies into universities, and I think it's been somewhat successful. Probably, I guess NSF probably would say it's been very successful. I just don't have great personal experience, so it's hard for me to know exactly how successful it's been. But when I guess when I think about programs that have happened really where industry has played a large role in university programs over a long time, it seems like there's very few of those to me. And again, going back probably 8 years ago, my experience at LSU was that was extremely hard to start up. And I look at the places that have been successful at this, and I think NCSA is a very good example, where the success has really taken probably, I don't know, 5 to 10 years to develop, and then it's been sustained over probably another 10 years, 15 years at this point. So I guess I'm not really sure that I have a very good answer to this. Again, NSF has some programs that try to support this, and it certainly is worth looking at those programs, but it seems like it really takes a lot of, in my opinion, a lot of energy and a lot of persistence to get these things going. So, I'm happy to talk maybe more during a break.
Well, in the interest of time, let's thank Dan so much again for